Welcome back. Let us continue the discussion on the turbulent scaling. So, we looked at free shear flows and also the wall bounded flows, where we looked at different region like inner region, outer region and overlap region. So, that is from there we will now look at the other pattern like the effect of some roughness and all these things, that this is where we stopped, that you can have an inner layer, log law layer, overlap layer and the outer layer. And then if you put them in the Reynolds number plot, there could be viscous sublayer, inner sublayer, buffer layer and all this. So, these finer details one can actually work out and look at in the. Now, we will move to the next set of things, that wall roughness on the turbulent bounded layer. So, what we are interested, this is if you have a boundary layer and there are roughness, then what is the effect of wall roughness. So, there could be different scaling law for inner layer, there would be friction factor. Now, to do the analysis, what one can look at it, it can be approximate the equation for the mean velocity, then they can have scaling laws, all the mean velocity like law of the wall, velocity defect law, log law, and then find out the skin friction coefficient and all these things. Now, if you look at the wall roughness, so what happens in the boundary layer? So, if there is a roughness with characteristics height S, then when you scale the velocity profile or velocity gradient, there would be another extra length scale that comes into the picture. And if someone look at the plots here, that this is nicely 64 by RE plot with the friction factor, and this is for smooth pipe, and as R by X increases, so you can see the effect of roughness. So, from smooth to the fully rough situation, and that is how the roughness is going to. Now, scaling over that outer layer, what would happen? Outer layer actually unaffected by the wall roughness. So, this is unaffected by wall roughness. So, the large eddies in outer region scale with delta, since S by delta is smaller than 1. Now, the scaling of inner layer depends on inner layer, it depends on S by delta V. So, if S by delta V less than 1, one can write Y by U tau del U by del Y, Y by delta V. So, this is for hydraulically smooth wall, or S by delta V, if it is greater than 1, then Y by U tau del U bar by del Y phi 1 R Y by S, which is again hydraulically rough wall. Now, when you talk about hydraulically rough wall, so here one can think about the friction at wall dominated by the pressure drag instead of viscous drag. So, in this case the viscous effect can be ignored. Secondly, the eddies which is close to the wall scale with the height of the roughness element. Now, in the overlap region of rough wall, one can write on the limit that phi 1 r y by s is delta tends to 0, phi naught y by delta 1 by kappa. So, if you look at the roughness effect on log law, so generalization of the log law for wall roughness. So, this is our u plus 1 by kappa y by s is by delta v with this factor which is 1 by kappa for s by delta v less than 5, if it is greater than equals to 7 it is 8.5. Or on the other way one can represent that u prime or u plus is 1 by kappa log y by y naught, and where y naught is the equivalent roughness height. Now, one can interestingly look at this b tilde versus s by delta v and that variation, and there is a nice database which is the experimental data one can see, and this is a smooth wall s by delta v 5 and this is fully rough beyond 70, and in between this goes through. So, this is from smooth to rough. So, in between this is a slightly mixed zone or the mixed situation one can expect. Now, second situation one can rewrite the logarithm law in the following form. We can write u plus or the 1 by kappa ln y by delta v plus 5.2 minus delta u plus. So, this will represent my logarithm law for smooth wall. So, we invoke that is the okay, that is my smooth wall effect, and then this is the displacement of the velocity profile due to roughness. So, it is essentially taking care of the smooth wall effect plus the variation due to roughness variation. So, for fully rough wall this would become 1 by kappa minus 3, that is s by s b 70. So, this will become 7.1. So, this is the same thing what one can plot for u plus by y plus, and you can see the difference is by delta v ratio and how the profile looks like. Now, also for this rough pipe one can find out the friction factor. From log law one can estimate the bulk and center line velocity. So, we have u naught minus u b by u tau which is approximated by 3 by 2 kappa. So, this one can try out. Now, we can estimate from the log law the center line velocity would be u naught by u tau would be 1 by kappa ln r by s plus 8.5, and the friction factor is equivalent to minus dpw by dx 2 r by this which is 8 u tau by u by square. So, essentially which brings f would be of this order, and if you put this thing in the plot which is f versus re, then this is the 64 by re curve and then the other curve one can, and this is for different s by delta v and this is for s by r by s. Now, if you go to turbulent boundary layer, so this is a flat plate, flow becomes turbulent here. So, this is our boundary layer profile. Here obviously V naught by u naught is quite small, that means the variation in the streamwise direction, and the free stream flow is irrotational. So, that will satisfy del u naught by del y minus del v naught by del x is 0, and also this boundary layer thickness del by L less than very much smaller than 1. So, 1 by L will be scaled as 1 by delta d delta by dl x. So, there are some assumptions which are kind of associated with that. One is the slow streamwise evolution, that means delta by L is quite small, that means in this direction the growth is quite faster. Secondly, it is a high Reynolds number case, so viscous effects on mean flow can be neglected except very close to the wall where the boundary layer and all this effect, and it can adapt itself to changes in mean flow, which is essentially the property of self preservation. So, now boundary layer thickness based on 99% of the free stream velocity we can define u bar at y equals to delta is 0.99 u naught, and Re delta would be delta u naught by nu. Similarly, one can find out the displacement thickness, which is the integral of 1 minus u by u naught dy, and Re delta star, and also the momentum thickness, which is theta x is the integral of u by u naught in dy and Re theta. So, these are the like momentum thickness, displacement thickness, and free stream velocity. These things are very standard and one can define those. Now, how we simplified the Gauni equation? So, we had continuity equation and momentum equation in 3 dimension in Cartesian coordinate system. So, no mean flow in z direction because of the symmetry. So, these terms goes off. Flow is statistically stationary, so the unsteady term goes off. Flow is statistically homogeneous in z direction, so these terms are also going off, and this also goes off, the complete z momentum equation. And also streamwise evolution is slow, we can use the same magnitude analysis for Reynolds stress. And now from here we can get our boundary layer equation. So, the boundary layer equation we get is that for free stream region, we have minus 1 by rho del p naught by del x, which is u naught del u naught by del x. Since v naught by u naught is 1. Now, we can integrate y momentum equation from y to delta and use 0 stress condition at the boundary layer top. So, that will give us p bar by rho, which is nothing but p naught by rho plus nu del v bar by del y minus v prime plus y to delta u bar plus by del y and dy. Now, you can take the derivative to x and make use of the continuity equation plus equation of the free stream. So, that will get us del p bar by del x u naught del u naught by dx plus nu del 2 u bar by del x 2 plus v bar by del x minus del x y by delta u bar del v bar by del x del v bar by del y dy. Now, we can substitute the pressure gradient into this x momentum equation, and what we get from x momentum equation plus v bar dy plus del x of y delta u bar del v bar by del x plus del y dy, which is du naught by dx plus del 2 u bar by del x 2 nu del 2 u bar by del y 2 minus del u bar v bar by del y. So, there are small terms which is a slow streamwise evolution of boundary layer or Reynolds stresses of the same of the order of. So, this goes off, this also goes off, and this goes off. So, from the approximate momentum balance we get u bar del u bar by del x plus del, which is u naught dx plus 1 by rho del tau by del y, where tau is rho nu now we can integrate this equation from wall to y. We guess tau by rho equals to u tau square minus u 0 to y plus where u tau is square root of tau 0 by rho. So, this is an friction velocity at the wall. Now, we use a boundary condition at the boundary layer top where tau delta is 0. If we put that, what we get is that tau by rho equals to u tau square multiply 1 by y delta plus u bar plus v bar minus y by delta v bar del y dy, where u tau square by delta is u naught dx minus 1 by delta 0 to delta u bar del u bar by del x plus v bar dy. So, this is what you get. For zero pressure gradient boundary layer profile, if we plot, this is how u varies and this is the y by delta. So, this is Blasius profile, and turbulent case, this is the variation of the u by delta, intermittency, tau by tau w, and that is the variation. So, total stress profile is approximately linear. So, one can think about similar scaling of mean velocity profile as for turbulent pipe. And now, if we go to the law of the wall, so there are multiple experiments and simulations have been done to find out or confirm this law of the wall, which is inner layer with y by delta less than 0.1. So, this is a plot for u plus versus y plus. So, law of the wall is u plus is a function of y plus. So, this particular zone where y plus less than somewhere 5, it is a viscous sublayer, then 5 to 30 is the buffer layer, then 30 to somewhere above 100 is log layer, where it follows this log profile, and this is the upper bound in wall limits of log region with increases of with x. Now, if we look at different layers now, inner layer what we have mean velocity profile, total shear stress tau by rho is nu del u by del y minus u prime v prime. Now, we can use Prandtl's mixing length hypothesis to get tau by rho equals to nu del u bar by del y plus Lm square, where del u bar by del y square. Now, we can normalize this one by delta v and u tau, so that we get tau by tau w is del u plus by del y plus Lm plus square del u plus by del y plus square. Now, once we solve for the velocity gradient, what we get, this by this equals to 2 tau by tau w 1 plus 1 plus 4 tau by tau w lm plus square, which is square root of that. Now, at the inner layer, tau by tau w is order of 1, which gets us back that this would be 2 by 1 plus 4 lm plus square to the power half. So, if we look at the inner layer mean velocity profile, so model for mixing length in whole inner layer for smooth wall, this is Lm plus is limit in log layer ky plus 1 minus. So, this is the Van Diest damping function, and that follows like this, which varies with the y plus, and u plus by y plus follows this line, where a plus turns out to be 26. So, there are evidences also with the measurements and simulations for this kind of profile, which are now, if you look at the mixing length boundary layer, which is a zero pressure gradient case, then the mixing length model gives you the Reynolds stress, the order of nu t and velocity gradient, which one can write Lm square and magnitude of the velocity gradient to the velocity gradient. And if you plot those things, this is how Lm is varying, this is how nu t is varying with y by delta, and this is the Van Diest model and for 0.11. So, one can recreate these things very nicely. Now, there would be velocity defect at the outer layer also. Now, when y plus greater than 50, we can have an velocity defect, which is u naught by u bar, which is normalized by u tau. So, this is for an fixed streamwise pressure gradient, and you can see when we plot this velocity deficit with y by delta, this is the line it follows, and this is the log layer. And if you only look at the normalized velocity profile, mean velocity profile with y by delta, this is how it follows, and there is a contribution comes from the wake. Now, this has a velocity defect law, we can find out. Now, let us say for y by delta greater than 0.3, the log law deviates from the velocity defect law, and the difference between two laws is the law of the wake. So, what one can write is that u naught minus u bar by u tau equals to f d y by delta equals to 1 by kappa ln y by delta plus b 1 minus by kappa w y by delta. So, this is our log law, outer scaling. So, this is velocity defect law, this is log law, and this is the law of the wake, where this is kappa b 1 by w 1, and here w is the wake function and this pi is the wake strength parameter or Coles parameter. So, you can have an alternative formulation which looks like u prime by u tau is 1 by kappa ln y by y naught plus pi by kappa w y by delta. So, this is again log law of the inner scaling, and this is the law of the wake. So, for complete smooth wall, velocity expression in the boundary layer would be u by u tau 0 to y plus 2 by 1 plus 1 square dy plus kappa Wy by delta. So, this gives you law of the wall with Bandiest model, this is law of the wake. So, this is law of the wake and this is law of the wall. So, then within the boundary layer you get complete profile. Now, we can find out the wake function. So, the law of the wake is universal function of y by delta, which is consistent with velocity defect law, and w y by delta would be. So, this is what for 5.5 you can see the wake contribution here. This is our velocity defect versus y by delta, and this is pi equals to 0.5. Now, we can define the wake strength parameter, wake strength parameter, and so it depends on, essentially depends on streamwise pressure gradient. So, you can write pi equals to pi beta, where beta is delta star tau w dp naught by dx, which is minus delta star u naught by u tau du by dx to the power minus 1, which you can think about the time scale of large eddies in outer layer. This is time scale of free stream flow. So, this is known as Clauser's parameter. Now, one important thing to note here, that turbulent boundary layers are self preserving. When this pi is constant in x, since in this case the large eddies in the outer layer can adapt to changes in the free stream flow. Now, if you look at for flat plate, which is a zero pressure gradient in streamwise direction, this would be almost half. So, again one can put these things and look at the wake strength. This is your u plus versus y plus, and this is increasing beta, say mild average, strong average, very adverse. So, depending on the, and this is the separating flow. So, you can actually define this, and this is how pi versus beta varies. So, you can actually define this wake strength, and if you look at for plane channel flow, this is the velocity deficit with y by delta, and this is our maximum deviation at y by delta, and this is the plot for pi, which is at different values. So, wake strength parameter of plane channel flow is small compared to boundary layer over flat plate. So, weak effect of pressure gradient on wake. So, we will stop here today and continue this discussion in the next lecture.